Hi there. This is a video about AC and capacitors and inductors, and particularly their phase relationships and why they exist. So I'm going to start off looking at just a simple circuit that's got a resistor and a capacitor and an AC supply. And just a reminder that throughout this entire thing, all voltages and currents that I refer to are all RMS. You could use maximum values for everything as long as you use the same. If you had RMS values, they all have to be RMS. If you have maximum, they all have to be maximum. But we usually use RMS. So if I put some values on this, now this is something would be good to do as an experiment, but just for the sake of the video, if we have a 12 volt RMS power supply with 50 hertz frequency and a 3.3 kilo ohm resistor and a 1 microfarad capacitor, in the circuit, if we measured this, you'd get a resistor voltage of about 8.6 volts. So the question would be, what would you expect the capacitor voltage to be? Well, it makes sense to apply Kirchhoff's voltage rule, okay, which is that the supply voltage should be equal to the resistor voltage plus the capacitor voltage, which would be, if we plug in the values we know the supply voltage is 12 and the resistor voltage is 8.6. The capacitor voltage is then just the difference between them, which should be 3.4 volts. The problem is that when you get a voltmeter and you measure it, it's actually more like 8.3 volts, which is like a surprising result, okay? Which is then leads to the question of like, why does that happen? That's like a disturbing thing. This is like Kirchhoff's voltage rule is based on conservation of energy. That's like fundamental physical principle. We can't violate that. So what's going on here? Why? So let's have a look at this in a bit more detail. If we take that same circuit and if we were to look at, if we were to connect like an oscilloscope or something like that, we can actually look at how the things are behaving over time. I'm going to relate everything to current. And this, it's sort of, some of the concepts are easier to understand if we relate them to current. So if we say we've got a sinusoidally oscillating current, and remembering that current is directly proportional to resistor voltage, so current and resistor voltage are always in phase. It means the resistor voltage will do the same thing, will also be sinusoidal. But if we were to actually connect this to an oscilloscope and compare it, we'd find that capacitor voltage is actually a little bit different. It's still a sinusoidal shape, but it's got a phase shift. We'd find that when the resistor voltage and the current are maximum, the capacitor voltage is actually zero. And vice versa, when the current and resistor voltage is zero, the capacitor voltage is at a maximum, or at a negative maximum. And just an explanation note here, throughout this whole presentation, all the graphs and phases and diagrams that I've shown, I'm making everything similar amplitudes just for ease of visual comparison, but that's not actually usually the case. Like, there's no reason that VR and VC have to be the same size. In fact, they would almost certainly not be the same size. It's just so it's easier to compare them. Now, the important thing to know is that when you use a voltmeter, like an AC voltmeter, the value that it reads is an RMS value. But the important thing here is that the resistor and capacitor are not using the voltage, or the voltage across them is not maximum at the same time. So there's a phase difference between them, okay? So we'll actually look at why that exists. So why is there a phase difference? We take our resistor and capacitor voltage curves. That's what they look like. Now, for the sake of the explanation, it's actually going to be easier to explain if we think about current. So if we think about current as being proportional to resistor voltage, I can kind of think of that resistor voltage one as like a graph of current. You shouldn't plot current and capacitor voltage on this necessarily on the same set of axes. It's not a voltage, but we're just looking at the phase relationship here. Now, important thing to remember here for the explanation is that capacitors oppose current flow due to charge building up on their plates. The more charge is built up on the plate, the more difficult it is to push more charge onto the plate. So, and that the capacitor voltage is proportional to that amount of charge. The more charge there is, the higher the capacitor voltage is, and the more it opposes current flow. So if we think about that point of maximum current, which is also where the resistor voltage is maximum, That's when there's minimum opposition to current flow. Now, there's two components in the circuit that are opposing current flow. There's the capacitor, which opposes because of charge buildup, and there's the resistor. The resistor is a constant effect. Okay, resistance doesn't change; it's constant, but the amount of charge on the capacitor is changing. So that does change. So when there's maximum current and there's minimum opposition, that will be when the capacitor is uncharged. Okay, there's no charge, and when there's no charge on the capacitor voltage is zero. That's why we get a peak in the current when the capacitor voltage is zero. Okay, if we want to think about the other end of the scale, if we think about that peak in the capacitor voltage, that occurs when the capacitor's got the maximum amount of charge, when it's fully charged. Okay, when it's fully charged, there's going to be maximum opposition to current flow, which is when we'll get our minimum current. We'll get zero current at that point, and our resistor voltage will also be zero. So current and resistor voltage, remember they are in phase. They are both a quarter of a cycle ahead of the capacitor voltage. The resistor voltage leads VC. Now, on these graphs, sometimes this can be a little bit misleading. People will look at a graph like this and think that the green one is ahead because it's sort of further to the right. People tend to think of this as like a set of waves moving from left to right, and the green one's in front. But in reality, what you've got to do is you've got to think of, as you go across the x-axis, which one reaches a peak first in time. And if you go across from the zero, from the left-hand side, the first peak you reach is the blue one, is the current, okay? So the current reaches a peak before the capacitor, okay? So current and resistor voltage are 1/4 of a cycle ahead, pi/2 ahead of the capacitor. So that's why we've got a phase difference. Now, Kirchhoff's voltage rule does apply, but you've got to apply it at each individual instant rather than like with RMS values, which are like almost like a time average. Okay. If we look at that graph again and we look at what happens at any particular instant, now we can apply instantaneously Kirchhoff's voltage rule, Vs equals VR plus Vc. Now, at time equals zero, when the resistor voltage is zero, the supply voltage must be equal to the capacitor voltage. So we'll mark that point, okay? If we go along a bit further, when the capacitor voltage is zero, when it crosses the x-axis, that's when the resistor voltage is maximum. So it must be equal to the resistor voltage at that point, okay? And then, so it's actually going to go along at any point where one of the values hits zero, the supply voltage will be equal to the other one at that point, which is always the peaks. So it's going to hit all of those peaks. Now, the point where the supply voltage will be maximum will be where the sum of those two is maximum, and the sum is going to be highest where they cross. So where the where the red and green lines cross for the first time, that will give us a positive peak in the supply voltage. And then we can go along and just mark. So it hits all of those peaks, and then it will be a negative peak where they cross again, and then it will hit the other peaks and another. We can mark all the points. So the supply voltage will actually look like this. Okay, so you can see that that's a sinusoidal oscillation. It's shifted across a little bit though, so it's got a slightly higher amplitude than VR and VC, and it's somewhere in between them in terms of phase. Okay. So just remembering, so just to summarize that, AC meters measure RMS values, and when you measure them, it appears that VR plus VC is greater than VS because the resistor and the capacitor are using that voltage at different times. Okay. It's much simpler. It makes much more sense if we look this, rather than looking at like these on sinusoidal graphs, if we use phasors, a phasor diagram. So if we take that same circuit, which had the graph we were just looking at, and if we draw this as a phasor rather than a series of sine curves. Now, by convention, the VR phasor, the resistor voltage, we draw that at the 3 o'clock position, and we draw everything else relative to that. Okay, so that's going to have that, and it will be rotating anticlockwise with an angular velocity, which is given by 2 pi f. Now, as we were just looking at, the capacitor voltage is behind the resistor. Okay, it reaches a peak after the resistor is shown in the graph on the bottom left. Okay, and it lags it by pi/2 by 90 degrees. That means in this we would draw the capacitor voltage downwards, at 90 degrees. Okay. Now again, I've just stressed again, I've drawn these as if they're the same voltage, same magnitude. They don't have to be. The resistor voltage could be much bigger than the capacitor or vice versa, but they will always be at 90 degrees to each other. Okay. So we've drawn here resistor and capacitor voltages almost like they're vectors. They have directions associated with them. Okay. That means we can actually find Vs, the supply voltage, by adding those two together, but we've got to remember that we have to add them like vectors. We can't just add the numbers, we've got to add the vectors, which means we would actually have to sort of draw something like this, okay, where the supply voltage is the vector sum of VR plus VC. And if we plug the numbers in there that we had before, the measured ones, 8.6 and 8.3, we can find the supply voltage, the value of it, using Pythagoras, okay? Rather than, we can't just go 8.6 plus 8.3 because those vectors, the VR and VC, are not in the same direction. But we can use Pythagoras to find it. So if we use Vs equals the square root of VR squared plus VC squared and plug in those numbers, we get actually 12.0 volts, which is exactly what the supply voltage was. We can also find phase angles using trigonometry in this. Now, it'll usually be a phase angle that you need to find with the supply voltage because resistor and capacitor are always 90 degrees to each other. Okay, the capacitor is always 90 degrees from each other. It's always pointing downwards. So, for example, you could be asked to find the phase between VR and VS, okay, which you would do using trigonometry, in which case theta you could say is inverse cosine of VR over VS. So it's 8.6 over 12, which is 0.77 radians. So in that case, you would say something like the resistor voltage leads Vs by 0.77 radians. Or just as validly, you could say Vs lags VR by 0.77 radians. Okay, so that's capacitors. Okay, you've got a situation there where the capacitor is opposing charge flow due to buildup of charge on its plates. And you get a 90-degree phase relationship there where the capacitor lags the resistor voltage, and you can add them together like vectors. Okay. Now we're going to have a look at inductors now. If we take the same sort of circuit but with an inductor in it, okay. Now, weirdly, inductor resistor circuits behave in a similar yet completely opposite way to RC circuits. So for example, if we measured the voltages in a circuit like this, we would get the same values if we had that particular value of inductor in there, okay? Which leads us to the same sort of like what's going on, sort of like surprise, you know, we're using more voltage than we're putting in there. It seems weird. Why is that happening? Because there's a phase difference again, okay? So if we plotted resistor and inductor voltage, we get a similar sort of phase relationship, except the inductor graph is around the other way from a capacitor. Capacitor started at the bottom, the inductor starts at the top with this, in this particular case. And now again, it's going to make more sense to explain this in terms of current. So current is in phase with the resistor voltage. So I'm just going to pretend that we're looking at current there. So we'll look at the relationship between current and inductor voltage. Now, the mechanism for an inductor is completely different than the mechanism for a capacitor. A capacitor is about buildup of charge on plates. An inductor operates because it induces a back EMF. Okay, a changing current causes a changing flux, and the inductor induces a back EMF that opposes the change in flux. And we have Faraday's law, or the inductor version of a Faraday's law, minus L delta I over delta T. Okay. Now, if we think about, look at the similar way. If we think about that peak in the current, the maximum current and therefore the maximum resistor voltage occurs at that point. Now, at the peak in current, the gradient of the current, like if you imagine if you're coming up that blue line, as you get towards the peak, the gradient of the line is getting less and less and less, and at the peak, the gradient is zero. It's a flat horizontal line. That means at that point, the rate of change of current, delta I over delta T, is zero. Okay. Now, if delta I over delta T is zero, that means technically at that point, the current is not changing. So at the peak and at the negative peak, like the top and the bottom of the current, the current is actually instantaneously not changing. That means there's no back EMF, which means at that point, the inductor voltage is 0. So when you have a peak of current, the inductor voltage is 0 because the current is not changing at that instant. Okay. On the other hand, the maximum inductor voltage occurs when there's maximum EMF being induced. That means the rate of change of current has to be maximum. Okay. That occurs where that blue line, the graph, has the steepest gradient. When the current has the steepest gradient, that is when it is changing the most rapidly. That occurs when the current is 0 and when the resistor voltage is 0. Okay. So the mechanism of inducing back EMF when the current is changing the most rapidly is why we get a 90-degree phase shift for an inductor as well. Okay. Except it's the other way around here. The inductor and the resistor voltage are a quarter of a cycle behind the inductor rather than ahead for a capacitor. Okay, so VR lags VL by pi/2. If we look at, we can also apply Kirchhoff's voltage rule in the same way as we did before, just real quickly. Supply voltage is equal to VR plus VL. So we can it hits all those peaks and doubles where they cross, and you get the same kind of relationship that we had, where the supply voltage is somewhere in between VL and VR and is slightly higher than either of them. Okay. Again, graphs like this get confusing to look at, so we'll look at it as phases. So if we take that same circuit, which had the graph we were just looking at, again, we start out with the resistor voltage at 3 o'clock, and everything else is drawn relative to that. It's rotating anti-clockwise with an angular velocity given by 2 pi f. Now, as we were just looking at, the VL phasor leads the resistor phasor by pi/2. That means the VL phasor will point directly up. Okay, and again, it doesn't have to be the same size. I'm just drawing them like this because it's easier to compare them. Okay. We could find this just like we did with capacitors. We could find the supply voltage by doing the vector sum of VR and VL. So if we did the vector sum of them, we find the supply voltages like that. And you can, if we had those same values, you can do exactly the same thing. You find supply voltage using Pythagoras, just like we did for capacitors, and you'd get the same answer. And you could also find the phase angle, okay, using trigonometry, which, because we've got the same values, we would end up with the same answer, 0.77 radians. The only difference in this case is that now the resistor voltage is lagging Vs. Before the resistor voltage was leading Vs, okay, because of the difference between a capacitor and an inductor. Okay, so we've looked at capacitors and resistors, and we've looked at inductors and resistors. What happens if we put all of them together in a circuit? Now things start to get a little bit confusing if we draw them like this. Okay, now why would we do that? The graph is just horribly confusing. So we're not going to look at it like that. We are instead going to look at it as a phasor. It makes much more sense. It's much simpler if you look at it as a phasor. Okay, so it's another way of representing the same thing, but it makes a lot more sense in this case. So we start off with our resistor phasor at the 3 o'clock position and rotating with an angular velocity. And we've put in the other phasors. The capacitor voltage lags the VR phasor by pi/2, so it's going down. And now in this case, I'm not drawing them to be the same size, just to be clear, because they don't have to be. The VL phasor will lead VR by pi/2, so it'll be upwards. And we can find Vs as the vector sum of all three of those if we add those together, okay? So if we went, for example, if we go up VL, then we go across VR and down VC, we end up with like a vector that's something like that, okay? We can find the value of Vs using Pythagoras, but we need to be careful about what values we use. That Vs vector goes across VR along the bottom, but up the side, the length of that side is actually the VL minus VC. It is the difference between VL and VC that matters, okay? So we could use Pythagoras with VL minus VC. And actually, in this case, I've drawn this diagram with VL being larger than VC, just to point out that that can be that way. But I could have drawn it just as easily around the other way, because that happens just as much, okay? In which case, you wouldn't, you would actually be able to use exactly the same formula. If VC was bigger than VL, then VL minus VC would be a negative number, but you're squaring it. So you'd end up with exactly the same answer anyway. So it doesn't actually matter which way around you do it. And you can find phase angles using trigonometry. Okay. And just a note there that that phasor diagram was done with VL being bigger than VC, but you could do it around the other way, and the same principles would apply. All right. So that's a quick rundown of phase relationships in circuits with capacitors and resistors, circuits with inductors and resistors, and then when you put them all together. If you can keep your head around this version, the LCR with everything in it, that probably makes the most sense, because then you can just leave out the one, like if you had a circuit like this and you didn't have a capacitor, you just leave the capacitor bit out and it works. If you have a circuit that doesn't have an inductor, you leave the inductor bit out and this works. Okay. All right. Thanks. Hope it helps.